Hello everyone. So this is going to be the last video of the first part, that's replication. We discussed about what single master DBs are. We talked about what happens when you have multiple masters, and the third part is when you have no masters at all, right? There were some problems in the previous systems, and this kind of tries to solve some of those problems. And of course, in the end, no system is perfect, so there are flaws with leaderless systems as well. But yeah, let's try to understand what they are and why do we need them. Okay, starting off with what the typical architecture looks like for a single master slave DB. So you have your client, right? It sends all the write requests to the master, and for all the read requests, it basically reads from replicas, right? This is what I discussed in the previous videos, and this is done because a lot of modern apps, they have they have more read volume as compared to write volume, right? So you use Instagram. There's a lot of people who just use Instagram and not post a lot, right? So you have a lot of people who want to consume content. These kind of systems are used a lot in those places, right? One of the bad part about this system is what happens if master goes down. Because we live in the real world, there are going to be instances when master is offline. In those cases, you really have to kind of block all writes, and you can still serve read content, but you really have to block writes for some reason. And one of the replica has to become master, and the client has to reroute their requests to that replica, and that replica will send those requests to other replicas. Basically, this is called a failover, right? So this is a problem in these DBs. Now let's move on to the next part. Okay, I want to talk about something called a leaderless system. You see, there are 4 nodes over here, okay, and these nodes all talk to each other. They all know, yeah, they know that everyone exists, and they communicate to each other. Now we have a client, right? The difference over here is that the client, when it sends a write request, it, instead of sending it to one master and then that master passing it on to the replicas, this client sends that request to all the nodes at the same time. And whenever it wants to read something, it also reads from all those nodes at the same time. Now this might sound confusing, but there are some very good reasons to do this. Okay, let's say the worst part in this system was that if you send a write to the master, what if the master is down, right? You can't process reads. But over here, let's say you send a write to node 1, node 2, node 3, and node 4, right? What if node 1 is down? Your system can still process writes. What if node 2 is down? What if node 1, 2, and 3 are down? Your system can still process writes, okay? So these systems are very highly available systems, basically. They are usually never down, because to be down, really all of your nodes have to go down. So you might also argue, well, what if I send my writes to node 1, and that node 1 communicates to all the other nodes, basically. But then again, we are going backwards, right? We are going to the master slave architecture altogether. The good thing about this again is that any node dies, you can still write to the system. Once you write to all of them, you want to get some sort of acknowledgement back from these nodes, right? Let's say I set my username, right, in some app. It's gonna send that message to all these nodes, and let's say it waits for any one of these nodes to respond. Okay, let's say node 2 responds back with an acknowledgement. The client can say, hey, we have your data in the system, right? We don't even have to wait for acknowledgements from other nodes, because once node 2 acknowledges back, that means that data is going to get replicated to all other nodes in some time, basically. For reading as well, we must query all these nodes, because what can happen is some nodes can get, they can get killed. There can be network delays as well. Some nodes might not have the most recent data. So you really need to query all the nodes. And from what data you get from all those nodes, you can basically see which is the most recent data, and that is what you can show on to the UI. And as I showed above, in your master slave DBs, you really need failover. There is no failover phenomenon over here because there is no master in the end. Okay. These are two questions you can think about. Does the client need to send updates to all nodes, or is one enough? One is not enough, because what if that node fails, right? So you really need to send your updates, writes to all of the nodes. And does it need to read from all nodes? If not, then how many? Let's say you send your write to node 1, node 2, node 3, node 4. Okay. Node 2 doesn't even read it. It doesn't even get that right, for example. Let's say node 2 failed, right? But you only read from node 2, for example. That will also cause a lot of problems, right? Because you are reading from a node that has stale data. So in the end, you really must write to all the nodes and you must really read from all the nodes. But this process is also kind of inefficient, right? Let's say you have 1,000 nodes, okay? Now, you want to write some DB change, right? You are going to send that, you're going to send the new content to all of the 1,000 nodes, but are you really going to wait for every single node to respond back to you? Like, wouldn't that really be very slow, right? Because what if a node dies? It might never respond back to you. In that case, you will be waiting forever, right? But what if you wait only for one node's acknowledgement? And that will make the system way more faster, but is that reliable enough? Is getting that response from one node enough to make sure that your reads are also not stale at all, right? This is a part that I want to discuss next in depth. How many reads, how many writes should we send to all the nodes? Because it's clearly not efficient, okay? This is where the concept of a quorum comes in. Now, quorums are a very critical topic in these distributed systems, basically. The idea about leaderless systems are that there is no leader, there is no central authority that says, hey, this is right and this is wrong, right? If you have 10 nodes and 9 nodes of them say that, the name of this person is Arun, one name says, no, the name of this person is Rahul, right? You really should listen to the 10 nodes, basically, because there can be delays, right? That node that says his name is Rahul, that node can be behind, basically. So you really have to listen to the majority. That's where quorums come in. Okay. For example, let's look at these 3 nodes. Okay, we have node 1, node 2, and node 3. There is a client over here. This client wants to send its writes to these nodes, right? And there is also another client that is going to read from these nodes. Okay, let's say this client is over here. Now I have a question. What is the minimum number of nodes that this client really should send its content to make it very clear so that when this client reads that data from DB, it doesn't read stale data, basically. Let's say this client is going to query to 2 nodes, basically. It's going to query this and it's going to query this node. How many nodes does the original this user is going to have to write to? It has to be 2, right? It could write to node 2 and it could write to any of these 1 and 3 nodes. So if this user writes to node 1 and node 2 and this user queries any of the 3 nodes altogether, we are guaranteed that this user is going to read the most up-to-date content, right? To do this mathematically, if you have more nodes, we can basically say that, let's say total number of nodes are n. Okay, the total number of nodes from which must acknowledge back a write is w, and the total number of nodes from which you can read is r. Okay, now as long as r is greater than n minus w, you will never read stale content. Let me just explain that very clearly over here. In this case, n is equal to 3 because there are 3 nodes, right? W is equal to 2. That means we are going to wait for any 2 nodes acknowledgement back. Well, this node obviously is going to send its write to 3rd node as well, but we don't even care if it acknowledges back or not, because node 1 and node 2 acknowledged back. Let's say this this request even failed in network, right? Node 3 never even got the right response. Okay, so we got two acknowledgements back, one from node 1 and one from node 2 basically. This basically means this: W is 2. Once we have two acknowledgements back from any of the nodes, we will tell to the user that, hey, your response was it was stored correctly in the DB, right? Now we have the third parameter R. Okay. Now as long as R is greater than n minus W, well, what is n minus W? It is 1, right? As long as R is greater than 1, we will never read stale data. What does that mean? That means that as long as we read from any number of nodes greater than 1, we will never read stale data, right? Okay, let me explain that. Let's say that this failed. Okay, node 3 doesn't have the right data. What this would mean is that if we query only one node, let's say we query node 3, right? That means we might be reading stale data, right? Because node 3 doesn't even have that data. But what if we read any two nodes over here? Let's say we read node number 2 and node number 1. Well, both of them have the data, so we'll get right data from both of them. What if we query node 2 and node 3? Well, node 3 has stale data, but node 2 has the correct data, so we'll get it. What if we query node 3 and node 1? Well, node 1 has the right data, node 3 has stale data, so we'll actually be, in the end, we'll actually get the correct data that we want. So this is what this quorum really means. This is a strong consistency. If you do that, you will never read stale data. I have a small example over here that you can think about. It's a pretty straightforward exercise. So let's say we have a client over here and we have 5 nodes. Now the quorum over here, the quorum over here states that, well, n over here is 5, okay, W over here is 3. So the client is really going to wait for 3 acknowledgements. If it gets 3 acknowledgements from any of these 5 nodes, we will tell the user that, hey, basically your write was successful, right? What should R be? Well, R should be greater than n minus W, which is equal to 2, basically. So what this means is that if a client 2 reads from any 3 nodes, right, it will always get the right data. Okay, let's say this client made some changes to the DB and these 3 nodes acknowledged back. Okay, now node 1, node 3 and node 5 have the most recent data. We have a client 2 over here. Let's say in the worst case situation, it queries node 4, it queries node 2, okay, and we must query more than 2 nodes. Let's say it queries any one of 5, 3 and 1. Let's say it queries 5. In this case, we are guaranteed that we will always get the right data because at least one of these nodes have the right data, right? In this case, it's node 5. So this quorum basically in a leaderless system, this quorum tells us that, well, if R is greater than n minus W, we will never be reading stale data. Okay. I also have some conditions over here. If W is equal to n, well, what is W? W is the total number of nodes that must acknowledge back the write. If we are sending our writes to 1000 nodes and we expect all our nodes to send acknowledgements back, we will be waiting forever, right? And that process is pretty slow. This would mean that the user can read the right data from any single one node. The reads will be super fast, right? We won't have to send reads to all the nodes, but the writes are going to be painfully slow, pretty bad over here. If W is less than n, so W is the total number of nodes that we need acknowledgements for, right? If it's less than n, that means we can tolerate failures. Now this is critical over here. When we were writing to these nodes, right, it could very well happen that node 2 died, okay, node 5 died. In this case, we had 5 nodes, but we can even tolerate 2 failures over here, right? Because we'll only be expecting W is equal to 3 results. So as long as any 3 nodes send back acknowledgements, we can tolerate 2 failures. So this is critical over here. That is why these systems are extremely high available systems. and if r is less than n, we can process reads if some nodes are down. The exact same logic. If some nodes are down, if any of the nodes are down, we really need to be sending this request to 3 nodes. It could very well happen that node 3 and node 1 were down, right? We sent our message to any 3 available nodes, 2, 4 and 5, and we were guaranteed that at least one node is going to have the most recent data. So our reads are also never stale, basically. Okay, let's move on to the next topic. Now again, let's read about what sloppy quorum is. Okay, I told what quorums are. Quorums are basically listening to the majority votes. This is not how the real world works, right? In real world, network issues are there, system breaks, there's just electricity cutoffs, right? Anything can happen. Also, in real world, let me explain it from here. In the real systems, let's say you have a Postgres table, right? The table is of terabytes of data. You are not going to store all of that data in the same DB, basically in the same node. Because this is not scalable. It's just a bad deal, right? You want to partition your data and store some parts of your data in node 1, some parts in node 2 and so on. Partitioning is a concept that I will make videos about in future, but just note that your data doesn't live in node 1, node 2, node 3 and node 4. That doesn't really happen in the real world, because it's just a wastage of resources, right? If you have your content on node 1, node 2, why do you really need it on node 3 and node 4, right? So that's how it works in real world, right? There's partitioning done. It's also called sharding. So databases are partitioned, and your data doesn't live everywhere in all the replicas. Okay. So these quorums that I told you above, these are inside the partitions basically. So I'll explain what do I mean by that. Let's say that we partition by the username. So we have user A. We want user A's data to really only live on 3 nodes, that is A, C and D basically. We have 5 nodes in the system, but we know that user A's content always lives on node A, node C and node D, right? The quorum over here, mind you, n over here is not 5, dude. N over here is not 5, n is actually 3 in this case. Okay, and let's say w is equal to 2. Okay, what this means is that even though writes are maybe sent to all of them, but we really need to read 2 writes from any 3 of these, A, C and D. We don't really care about B and D, right? Because that's not where A's data even lives at all, right? In this case, what can happen is that, just a second, right? In this case, what would happen if let's say C goes down, for example, okay? There were 5 nodes in total. C went down, but we needed, let's say C and D went down, okay? There were 5 nodes in total. We needed at least 2 writes, basically, two acknowledgements, right? C and D went down. We got 1 acknowledgement from this A, but C and D were not able to give us acknowledgements, right? So will we stop writing over here? Really depends on how you design the system over here. You can block writes if you want, but sometimes to make the system very high, to make it very available, what you do is, even if you know that A's data doesn't live on C and D, you can store that data temporarily on these nodes, B and D basically. So you will be accepting writes from any one of these, basically A, B and E. In the end, let's say A and E acknowledge back. You will tell to the user that, hey, your data is present in the system. Whenever C and D come back online, this E will transfer that data to C and D, and A already has it, right? This transference of data is called hinted handoffs, basically. So this is what really happens in the real world, okay? And now moving on to the last topic of leaderless systems. We will be talking about concurrency. Because concurrency is a big part, if you think about it over here. Just a second, let me have some water. In leaderless systems, what happens is that there can be multiple users editing things at the same time, right? Let's think about this. Let's say we have 3 nodes over here, and yeah, let's say we have 3 nodes over here, and we have 2 clients. Okay, client 1, this these axes basically represent time. Okay, client 1 set a key A, okay, and client B is setting a key B. Now client A sent this set request to, let's say, node 1, 2 and 3, and you can see it in green arrows, right? B, client 2 also sent these requests to node 1, 2 and 3. The request to node 3 failed, which is fine, because let's say W was 2 in this case. Both these users got acknowledgements back from at least 2 nodes. So we would have shown the users that they got the right acknowledgement, okay, that the write was successful. In this case, if you think about it, if client 2 does a read of this key, right, it's going to get some weird results basically. So as you can, let's check it. Let's check node 3. Okay, this set key is equal to B failed, but we got the correct, but it was updated successfully from client A. So client 2 was going to read A basically from node 3. Okay, from node 2's perspective, this set key is A reached it earlier basically. Maybe network was fast or anything at all really. This reached node 2 late, and that's why node 2 returns B. Okay, node 1 basically, client 2's request reached it earlier than client 1's request, and it showed A, right? So client 2 is basically going to read different results from different nodes basically, and this is a very common thing. To solve this, we can follow a pretty straightforward approach. That is, in any of these nodes, we can have a strategy called LWW, which basically means last write wins, right? Would have some sort of timestamp, some sort of logic that really makes these changes in different nodes coherent, basically. So whatever write was later in the time, that is the kind of write that we store, right? But this also has drawbacks, of course, because clocks are never 100% accurate in distributed systems. Clocks can drift away, right? That's number 1. Number 2 is clients can get acknowledgements. Let's say, okay, talk about client 2, right? Client 2 got an acknowledgement that, hey, your change is written, key is set to B, but if you look at the reads, well, it's still getting A, right, in this case. So we can be showing the wrong message to clients, even though, and we can basically keep discarding whatever they are writing in last write wins. So that is one of the way what happens. The second way is to kind of merge the changes together in some way, right? And that is called versioning. It's called version vectors. That thing is another topic which is out of the scope of this video, but you can learn more about that. Yeah, and I've written over here, for most simple processes, you can have last write wins, and you can also read about version vectors. So this is a big topic, how concurrency is controlled in leaderless systems. And usually what really happens is last write wins. Whichever write reached the nodes most late, I mean, whichever is the most recent write, we just use that and we discard all remaining writes. That's the most simplest strategy. But if you need more than that, you can use version vectors. This is way better in a lot of different ways, but because this kind of keeps on combining whatever changes you're getting from different clients. So yeah, that is about it from my end, and in the next video we will be diving into different topics other than replication. So yeah, thank you so much.